So next is the trigonometric functions of sums and differences of angles, two angles actually. Now, before we see how to prove this result, let us recall something that we have already seen. Namely, these identities does not matter what x is any real number, but sine of minus x is minus sine x and cosine of minus x is cos x, is the same as the cosine of x. So we will need these two identities to prove that one. So here we see the sum of two real numbers, or you may regard them as angles because we are talking about trigonometric function values of them. So what is the cosine of x plus y? That is cos x cos y minus sin x sin y. So let's now see how to prove this. Okay. See, because we have to talk about cos x, cos y, cos x plus y, sin x, sin y, so obviously we will need the unit circle because that's how we have defined these functions. So accordingly we choose our axis, x axis, y axis, and we have chosen the unit circle whose center coincides with the origin of this coordinate system. This means that this point where the unit circle crosses the x-axis has coordinates 1, 0. Alright, so let us now next what we do, we put the angle x in the standard position. What does that mean? It means that the initial line of the angle x should coincide with the positive x-axis and the final line is whatever it is. In the text, the angle x has been chosen in such a way that the final line lies in the second quadrant. This is of course not necessary. This is just one of the many cases. But let's just see the proof in one case and then we will have a brief discussion about how one can go for proving the other cases. So this is the final line or the terminal line of the angle x. And there is another assumption that we are using here, and that is that x is positive because the rotation is anticlockwise. Say this point where the terminal ray or terminal line, whatever you want to call it, cuts the circle, let this point be P1. Then we know what the coordinates of P1 are. Cos x, sin x. In fact, that's what cos x and sin x are by definition. Next, what we do, next we consider the angle y but not in the standard position. We are going to choose the initial line of y as the terminal line of x and say this is the terminal line of y. And here again we are using the assumption that just like x, y is also positive. So here also, despite y not being shown here in the standard position, but the rotation is anticlockwise because y is positive. That is another tacit assumption. It has, the book doesn't say anything explicitly about these assumptions, but the diagram that you find in the book, looking at the diagram, these assumptions become clear. So this is your y. Again, anticlockwise rotation, but not in standard position. So this is your y. Now, y is positive, so an equal angle Equal angle means whose magnitude is also y, but where the rotation is clockwise. That means that angle will be minus y, can also be drawn. That, however, the authors have chosen to draw in the standard position. So what we are now going to see is this. So this is y not in standard position. Now let's think of minus y, but in standard position. So in standard position means for the angle minus y, the rotation will start from here and then it will come like this. Okay. Say the terminal line of minus y is this. All right. So this is our minus y. Magnitude of these two angles, this angle and this angle, are same, and that is why, but they are of opposite sign because the rotations are different in two different senses. All right, so let us name these other points of intersection also. I don't exactly remember which one is which in the text. Let me just call this P2. It does not really matter what we call these things. And let us call this one P3. All right. Now you can see that the angle x plus y is this angle whose initial ray is of course the x-axis, positive x-axis, and the terminal ray is OP2. Oh, I did not name the origin. It's understood that the origin is O, but still we have to write. So the initial ray of x plus y is this OX, and the terminal ray is OP2. So again, from the definitions of our trigonometric functions, we can write the coordinates of P2, and they are, the x coordinate is cos x plus y, and the y coordinate is sine x plus y. So these are the coordinates of P2. And similarly, we can also write the coordinates of P3, which I will write on this side. And they will be cos minus y, comma, sine minus y. Do not make one mistake, okay? And that mistake is that you say you want to write the coordinates of P2 and you ended up writing cos y comma sine y. No. Whatever coordinates of these points on the unit circle you want to write, they should come from angles which are in standard position. These coordinates have come from the angle x, which is in standard position. Its initial line coincides with the positive x-axis. The initial ray of x plus y also is the positive x-axis, and the initial ray of minus y is also the positive x-axis. Then only you can write the coordinates of these points like this. Okay. And because we have named these points like this, let us also call this one P4, whose coordinates of course are 1 and 0. All right. Next what we do, next we join some points. Let us join P1 and P3 by a straight line segment. I have not shown the line fully because it will interfere with this y, but you understand that it's there. Or if it looks very bad, let us write y somewhere else. Yeah, and this angle is of course y. And let us also join P2 and P4. And here also we will have that problem. So let's just clean some parts as much as we can. Let us first join the points and then we will write whatever was there. Okay, so this angle is minus y. And of course, besides that, we had O. Should not write O, here we should write O close to the origin, but because the origin is cluttered with other things, we have written O there. So this is the setup. Now the diagram looks quite complicated, but because we have gone through the steps of drawing this systematically, we now understand what the different parts mean. Alright. Now what are we going to do with this? The claim now is that you may see that there are two triangles in this diagram. One of them is P1O P3, this one, and the other one is P2O P4, this one. A triangle which is somewhat vertical and another one which is somewhat horizontal. The claim is that these two triangles are congruent. Let's see why. And you do understand that you cannot just simply draw the diagram and not say anything. I have said it, but you need to write all these things, which I am not going to do. This is the way, it's already given in the book, but you should write like this, whatever steps you went through in drawing this diagram, you should write like this. Let us consider a unit circle whose center coincides with the origin of our coordinate system, and then let P4 be the point 1, 0. Perhaps we should not say anything about P4 in the beginning itself. Let X be put in the standard position. Let the terminal line of X it crosses the unit circle at the point P1. So the coordinates of P1 are cos X, sin X. So all those things you have to write. And then you come to this claim. The claim is this. The triangles P1O, P3 and P2O, P4 are congruent. You can see one thing immediately, namely that already two pairs of sides of these two triangles have equal length, are of equal length. For example, P1O is the same length as, say, P2O. Why? Because they are both radii of this circle. Actually, it's 1, that length is 1. So this side is equal to this side. This side from this triangle and this side from this triangle are having equal length. Similarly, P3O has the same length as P4O, and that's also 1. That length is also 1. So we have found pairs of sides which are of equal length from the triangles. Now, if we can find an angle which, a pair of angles in the triangles which are also equal in magnitude, then by side angle side, that theorem, the triangles will be congruent. And that angle is from this triangle P1O P3, that angle is P1O P3. And from that triangle, that angle is P2O P4. But, oh, there is a small mistake in the drawing. This rotation doesn't stop at the y-axis. It continues to this line. Okay. Now, how do you prove that these two angles are equal? Note that angle P1 O P3 is equal to angle P2 O P4. But how? Okay. Now, you can see that the angle P1 O P3 is a combination of two angles. One of them is this y, which is P1O P2, and the other one is this small angle which comes after that. Let us call it theta. Consider the angle theta, which is P2O P3. Oh, and there is one more thing that I must mention here. You see, whenever we are talking about trigonometric functions, there, when you put an angle or a real number, same thing, in radians, okay, as input, there you take care of whether the number is positive or negative or those things, okay. The sign of the number should be, you should have no confusion about that. You may have negative sign. However, when we are talking about congruence of triangle, and for that, when we are talking about these angles, these are geometric angles, okay, not related to rotations. These angles that right now here, these angles we are writing here, they are geometric angles, they cannot be negative. So, this theta is actually just our ordinary angle from plane geometry, not related to any, I mean, you can think of an anti-clockwise rotation so that it becomes positive, but forget about those things. Just like the angle P1O P2 is simply y, and the angle P3O P4 is also y. It's a negative angle, but the magnitude is y. So we are talking about magnitudes here. In that sense, theta is P2O P3. All right. Now, do you see this? Angle P1O P3 is y plus theta, y and theta. This angle and this angle gives you this angle. Also, P2 O P4 is theta plus y. That's why I said magnitude, okay. We are, however, not writing anything wrong. I mean, we are thinking of magnitude, but you may be thinking that I am writing something wrong. No. Here, the assumption is that y is positive. That is why we are disregarding the minus sign here and writing simply y. Okay, so in this sense, this geometric angle has magnitude y. And they are the same, so that's why they are same. And that's how, besides having pairs of equal length sides, the triangles also have a pair of equal angles. And that is why they are congruent. Now, because they are congruent, there are other pair of sides which we have not talked about yet, which is P1, P3 from this triangle and P2, P4 from that triangle, they will also have equal length. So now we consider that fact. I cannot lose the diagram now itself, so let me just keep it. That's why I have to use this part. So now that we have understood the triangles are congruent, let us use the fact that P1, P3 is equal to P2, P4. So P1, P3 is equal to P2, P4, which implies that P1, P3 square is equal to P2, P4 square. Why square though? That's because now we will use the coordinates of these points P1, P2, P3, P4 to calculate these side lengths, and in doing so we will use the distance formula for the distance between 2 points in a plane whose coordinates you know, and you already are familiar from the about the distance formula from your earlier classes. And in the distance formula, let's just quickly recall what the distance formula is. Say you have 2 points. This is one point and this is another point with their coordinates shown like this. Then the distance d between them is given by this formula. Whether you want to write x1 minus x2 or x2 minus x1 does not matter because there is square. Okay, so you will get the same value. Now, because the original distance formula involves this radical, this square root, to get rid of that, that will be somewhat unnecessary to what we want to do here. That is why we have chosen square. So, let us now calculate these squares of distances. Okay, so everything is now ready. So we just have to calculate these two quantities. Let us first calculate P1, P3. I mean its square. So for getting the radical, we just have to take the sum of the squares of differences. The x coordinates of P1 and P2 are cos x and cos minus y. So cos x minus cos minus y square. Then the y coordinates are again sin x and sin minus y. Sin x minus sin minus y square. Yeah, never forget that here we have difference, so we have minus. We will take care of this minus y afterwards. I mean in this next step. And this is where those first two identities will be used. Cos minus y is simply cos y. Sin minus y, however, is minus sin y. With this minus, that will become plus. Alright, now if you expand these squares, you are going to get cos square x plus cos square y minus 2 cos x cos y, and expand this one also, plus sin square x plus, now I need to use that part, to at least write this calculation, plus sin square y, because it is a plus b whole square, so plus 2 sin x sin y. Okay. Now let us group the terms so that we can simplify the expression. Cos square x plus sin square x, they give us 1. And that is something we already know, okay. Similarly, cos square y and sin square y give us another 1. So these two ones give us 2. So we are getting 2. And along with that, what else have we got? Minus 2 cos x cos y plus 2 sin x sin y, which we can also write like this: minus 2 times cos x cos y minus sin x sin y. Okay. All right. But what shall I do now? I mean, I need some space. So now I have to get rid of the diagram. But of course, I cannot just simply erase it now itself, because we have got only P1, P3 square. What about P2, P4 square? Let's just write the coordinates of these points, because that's all we need to calculate the square of distance, and erase the rest. Cos x plus y, comma, sin x plus y. So these are the coordinates of P2, and the coordinates of P4 are 1 and 0. So now we can calculate P2, P4 square. So P2, P4 square is going to be cos x plus y minus 1 square plus sine of x plus y minus 0 square. All right. So this is going to be cos square x plus y plus 1 minus 2 times 1 times cos x plus y, so this. And this is a lone term, so it is simply sine square of x plus y. Now here also cos square x plus y and sin square x plus y will give us 1. That one and this one will give us 2. So we get 2 minus 2 times cos of x plus y. And these two squares are equal. That means this expression is equal to this expression. So let's just write that next. So 2 minus 2 times cos x cos y minus sin x sin y is equal to 2 minus 2 times cos of x plus y. And this thing implies, if you do the cancellations, I mean, there will be some steps which you understand, okay. Ultimately, you are going to get this. I mean, having gone through school algebra so much, it's okay if I skip these steps. It's also okay if you skip these steps. But if you want and you have some confusion, you can write the intermediate steps. That first you cancel 2 from both sides and then you divide both sides by -2. So those things you can do. So that's how we have proved this identity. And this identity is true for any real numbers x and y. Oh, and did you notice one more thing? X and y are in radian, because in the proof we have used our standard definition of the trigonometric functions, and that's why we have been, well, I should not say we have been able to, but we had to use the unit circle because that was the definition. But actually these formulas are true for degree measure also. But it's advisable that you forget about degree measure. You invariably think that in whatever discussion we are going to have from now on, whenever trigonometric functions appear, the input is in radian. Okay, but this brings in another problem. Actually, although the proof is over here, but really, strictly speaking, it's not over. Why? Why is that so? Well, that is because, do you recall that we made some assumptions in the proof about which nothing has been said in the text also? Namely, these are the assumptions that we made. X was positive, y was also positive, x lies in the second quadrant, okay, and y is also such that after the rotation that the terminal line of x went through, then we had the rotation for y, and even then x plus y lies in the third quadrant. All these things matter, and they somehow shaped the proof the way we had it. But you can understand then that there are so many other cases. In fact, what about the cases where, say, x is negative or y is negative, or x and y are both negative, and if they are of opposite signs, say x is positive and y is negative, x plus y itself can be either positive or negative or 0. That's also possible. No, x can be minus y. So many cases are still there. However, the text only shows one case. What does this mean? Is it just like we are being fooled by the authors? Well, not exactly that. But the thing is that those other cases also can be proved similarly. If one wants, one can go through, say, one of these other possible cases. There are many others that I have not even mentioned. Say x is positive and y is negative, and x plus y is positive. Then for that also, one can write a similar proof. Similar but not exactly the same, because the diagram will have to be adjusted. But if someone is a little clever, then one can somehow get the proofs of these other cases from what we have done in this case itself. Manipulating x and y, their signs. So, without going into those complexities, right now let us assume that in these other cases also this same identity is true. We have to assume that right now. And that is why, do you remember that in the beginning of this entire trigonometry thing, I said that this is only one way of defining trigonometric functions, that is using unit circles and all those things. There is another way and a better way where we do not have to rely on any geometry for defining these functions. And when one uses that definition, this identity can be proved in all the cases and in a much more simple manner than what we did today. Though that definition or those definitions, however, are college level definitions. Okay, we have nothing to do with them right now, but those are much better definitions. But anyway, we now have this identity, so let's now use this identity to see what other identities we can derive from this. And the first thing we can derive is the formula for cos x minus y. We now have x plus y, so from this we can easily get cos x minus y. How? Let's see. Actually, it's almost immediate. This is the formula cos x minus y. You may see that when you have a plus here, you have minus. Here you have minus, so the corresponding formula will have plus in the middle. Cos x cos y plus sin x sin y. But let's prove this. Okay. This is not 2, because we started with those first two things. This is the third one, and this is 4. So let's use the third one. We have cos x minus y equal to cos of x plus minus y. I mean, x minus y is also a sum, the sum of x and minus y. So here we can use our third identity and write cos x cos minus y minus, because the third identity has minus, minus sin x sin minus y. But now you use your first two identities. Cos minus y is cos y, so this term does not change. However, sin minus y is minus sin y. That minus and this minus will give us plus. And that's how here we have a plus in the middle. Okay, so not just cos x plus y, we now have an identity for cos x minus y as well. And then what else do we have? Okay, but then what can we say about sine? We would want similar formulas for sine also. What to do about that? So let's just do a trick here in the form of this fifth one. So the fifth one is cos. So we are now going to take a special angle, pi over 2 or 90 degree, minus, I am repeating one thing again, that whatever we are writing here are true for degree measure also. We have just had the proof using the radian measure, but of course you can convert the angles into degree, and when you do so, you will see that the exact same formulas are true. But we prefer radian because eventually we will have to see calculus, and there radian is the preferred measure. You will see why. So that's why we write pi over 2 minus x. It turns out that this is sin x. Let us see how. Everything is so easy now that we have these formulas. We just have to use the formula. Oh, so here we will be using which one? I mean, we of course will start with this side. We will be using this formula cos x minus y, where we have a plus in the middle. Cos pi minus 2, pi over 2 minus x. So this is cosine of pi over 2 cosine of x plus sine pi over 2 sine x. Cos pi over 2 is 0. Sine pi over 2 is 1. So this term vanishes and this term becomes sine x. Okay, so that's how we have our fifth one. Similarly, we have a sixth one also, where we start with sine and that gives us cos x. Now you see that if you straight away go for proving this one in a similar manner, in the beginning itself you have to stop because you do not have a formula for sine x minus y. In fact, that's what we want to have, and these are some things that we are doing to get to that. So then what do? Now we can do a trick here. We can use the fifth formula with pi over 2 minus x in place of x. So if you start with this left hand side, no. So in a sense, actually you are starting with the right hand side of that formula, but now in place of x you have this. So if you keep that in mind, then you can write like this. Sine of pi over 2 minus x is equal to so think of this here, then that same thing should appear here now if I write cos and use the fifth formula. Then this should be equal to cos pi over 2 minus pi over 2 minus x. So we are simply using the fifth one, and this is nothing but cos x. So that way we have the sixth one also. And now we can cleverly use this fifth and sixth one to have the addition and subtraction formulae for sine as well. And the next one is just that. So these formulae, this fifth one and sixth one, actually allow us to convert sine into cos and cos into sine. And let's next see sine of x plus y. Unlike the cosine formula, where besides having that alternating signs in the middle, you also you go back to those formulas, you see that in one term we have both cos x, cos y, and in the other term we have both sine x, sine y. Here the terms will be mixed. With sine x we will have cos y, and with cos x we will have sine y. Sine x cos y plus cos x sine y. And here we do not have alternating signs. You have plus here, you have plus here. You can devise many ways of remembering this formulae, but in the beginning itself, you should not bother too much about ways of remembering them. Okay, you just have them the way they are. and use them again and again instead of blindly memorizing like a chanting, no, like sine x plus y is sine x cos y plus cos x sine y. You say that 100 times and you will remember. That's a very bad way of trying to remember something. You use these formulas, you play with these things and see what they do, and always keep the book open so that every time whatever you want to do with this formula, you see whether what you are using is correct or not. That way you will remember them better and you will actually remember them. Okay, so let's now prove this. Now that we have a device of turning sine into cos and we know what cos x plus y is, so everything becomes so easy now. You see, this is how you can prove this. Okay. So what we can do here is we can write in place of sine, we can write cos, and we can write this. So we are using the fifth formula here. And now you will use the addition formulae for cosine, but that also a little cleverly, not blindly. So what we next do, we couple these two together, pi over 2 and minus x, and keep minus y separately. If you want, you can keep pi over 2 and y also together. It's up to you. So now you use your cos x minus y formula, which is cos of this times cos of y. With cos, we have both the factors cosine in one term. And whenever you have minus, you have plus here. The signs alternate. And then in the other term, both are sine. Sine y. So cos pi over 2 minus x is sine x, and this is cos y, plus just like that sine pi over 2 minus x is cos x, and that is sine y. So using the fifth and sixth one, we now have a formula for the for the sine of a sum of two angles. And once you have this, you can consider the difference also. And for the difference, for establishing this formula, you do not even have to do all these things. You can use this seventh one immediately. And this one will be sin x cos y minus cos x sin y. So the formula for the difference of, for the sign of difference, minus, you have minus here, you have minus here. No altering sign. The rest is same. Sin x cos y, sin x cos y, cos x sin y, cos x sin. There also, in case of the cosine formulae also, the terms remain the same, cos x cos y and sin x sin y, but the signs change. They alternate. Here the signs do not change. So how do we establish this one? Again, just like how you had the formula for cos x minus y, here also you write x minus y as a sum, the sum of x and minus y, and use your recently obtained formula. So this is sine x cos minus y, you have plus here, so plus here, cos x sine minus y. And then you recall your first two identities. Cos minus y is simply cos y, but sine minus y is minus sine y, so that minus sign will come in the middle. And that's how you get this minus. Minus cos x sine y. Okay, so we now have four formulae. The sum of two angles, the difference of two angles, they are sine and cosine. Now, just like that, you can have many other formulae. In fact, the book notes these ones. One can similarly prove using the sine and cosine addition and subtraction formulae these things, these special things. Cos pi, I don't like to remember these things. I mean, I remember the four, but these ones I don't remember, and I don't even put any effort to remember, because you can use those formulae and quickly know what this thing is. For example, this will be cos pi over 2 cos x minus sin pi over 2 sin x. Now, cos pi over 2 is 0, so the first term vanishes. Minus sin pi over 2 sin x, sin pi over 2 is 1, so that's why you have minus sin x. It does not take really any time to figure out what this side will be. So let me just simply copy these things. Just like that, you have sin pi over 2 plus, I don't think there is any point in trying to memorize these specific things. Some people do for some purpose, but I don't, I never did. Rote memorization should actually be discouraged as much as possible, especially in mathematics. See, this part is so boring, I don't feel like writing also, because I have to copy now. This is so frustrating. Okay, instead of writing, let us just do it ourselves. Okay, I don't really know, I mean, I have it here, but I don't really know what this side is. So let's apply the formula. The formula is cos pi cos x, because we are writing for cosine, so cos cos sin sin. You have minus here, so you will have plus here. Sin pi sin x. And you may actually have some difficulty in remembering these values also. That's not a problem. You go back to your unit circle. For these special angles, it's really easy to figure out what it will be. What is the angle pi? This angle. So your initial ray, of course, is this in standard position, but now the final ray is this. That means this is the point where the final ray intersects the unit circle. What are the coordinates of this point? -1, 0. So the first one is cos and the second one is sin by definition. Cos pi is -1 and sin pi is 0. So that way you have minus cos x. It should be, yeah, it is minus cos x. Similarly here also, while I mean if you want to expand this using the usual addition formulae, you will need to know cos pi over 2 and sin pi over 2. This is your pi over 2. So the terminal ray is the positive y-axis. The point of intersection of that one with the unit circle is this. Its coordinates are 0, 1. So cos pi over 2 is 0, sin pi over 2 is 1. It's that easy. And there are quite a few others. Okay, I won't write those things here in this ninth one. You can see the text. Instead, let us see the next part. What about the tangent function? What about tan x plus y? Now, so far, whatever we did not have to say anything about x and y, in the sense that we did not have to restrict them in any way. They were allowed to be any real number. That is because sine and cosine are defined for all angles, but tan is not like that. That's because you already know why that is so. The definition of tan x is this, right? So the only problem is if cos x becomes 0, then tan x is undefined. And cos x becomes 0 when? Precisely when x is an odd multiple of pi over 2, where n is an integer. I mean, this is how a general odd number looks, right? 2n plus 1. It's an integer which if you divide by 2 will leave remainder 1. That by definition is an odd integer. So it looks like that. So these are precisely the inputs that we have to avoid when talking about tan, because their cosine becomes 0. So accordingly, whatever formula you are going to next have about tan, that should take care of this thing. And that is why here there is restriction. And that restriction is this. Let me start from there. It's the 10th one. If x, y and x plus y are all different from any odd multiple of pi over 2, then this is the identity. Tan x plus y is tan x plus tan y divided by 1 minus tan x tan y. We want x and y to both be not any thing like this, because we want to write tan x and tan y. Also, we want x plus y to also not be anything like this, because we want to write this one. But now how do we get this formula? That is simple. You just apply the definition of tan and then apply the addition formulae for sine and cosine. So the proof goes like this. So let's see if we really get that. With those above restrictions, we do not have to worry about denominator becoming 0. It won't be 0. So we start with this. And the meaning of tan is just this ratio. You know, whenever you are doing something in mathematics now, the more you see these symbols, they take on kind of a status like a mysterious quantity. You think of tan as an entity. I mean, it's a function, but also do not forget what it actually is. It's actually, although it looks like something different, something I don't understand, just like that a feeling comes. But never forget that tan is just another way of writing sine divided by cos. That's it. If you do not lose track of these things, maths will be very easy. So let's apply the formulae that we have found today. The numerator is sin x cos y plus cos x sin y, and the denominator is cos x cos y minus sin x sin y. And again, let's see that we were devising some little rules for remembering this formula, right? When it comes to sine, it is sine cos cos sine, mixed terms, and the sign does not change. Here you have plus, here you have plus. When you are expanding cos, it is cos cos and sine sine, and the sign changes. It is plus, it is minus. Okay. Now, because x and y are not multiples of pi over 2, so cos x is not equal to 0 and cos y is also not equal to 0. And that is why you can divide the numerator and denominator by cos x cos y, because they are not 0. And if you do so, and if I write the terms like this, say I have done that division, and now below everything cos x cos y appears. Cos x sin y divided by cos x cos y. In the denominator also, cos x cos y divided by this minus sin x sin y. Actually, truly speaking, no. If you want to do things rigorously, you have to write all the reasons alongside the steps. You write here beside this step that we have divided the numerator and denominator by cos x cos y, and the justification that it can be done because cos x and cos y are both not 0. These things, truly speaking, have to be done. But sometimes out of laziness we don't do. But in exam you write everything, okay? As clearly as possible with as much detail as you can provide. Okay, so now here you have cancellation, but there is something about presentation that I should add here. You quit doing these things, okay? Don't do it. I mean, you used to do it in lower standards, but now don't do such things. It looks very bad. It's only something that helps us remember what we are doing or what we are going to do, but don't make that a part of your solution or proof. It is like this, keep it here. In the next step, you will write 1. Sin x divided by cos x is tan x. Cos y cancel out. And again, because cos y is non-zero. Here cos x and cos x cancel out, and sin y divided by cos y is tan y. Here everything cancels out and you have 1. Sin x divided by cos x is tan x, and sin y divided by cos y is tan y. So that's how you have your addition formula for tan as well. And just like the ones for sine and cos, here also you can derive from this itself another one for tan x minus y. So let's do that also, and then we will stop for today. Again, if x, y, and this time x minus y are not odd multiples of pi over 2, then there are better ways of writing a sentence like this. Okay, I should have perhaps have written, if neither of x, y or x minus y is an odd multiple of pi over 2, but you can adjust the language. Then tan x minus y turns out to be tan x minus tan y divided by 1 plus tan x tan y. So let's substantiate this one also, and then we will call it a day. X plus minus y. Now there is a very little thing which is so small that it is easy to ignore it. And that thing is that whenever you apply some formula or some result or some theorem somewhere, always make sure that everything that the theorem requires is true. That is, all the hypotheses are true. What are we going to write here next? We are going to apply the previous one, that is the 10th one. Do we have all the conditions that the 10th one requires? It requires that x and both the angles should be, none of them should be any odd multiple of pi over 2. It is given that x and y are not odd multiples of pi over 2. But what about minus y? Because we do not exactly have y here, we have minus y. Yes, minus y is also not an odd multiple of pi over 2. It's very easy to see why that is so. That's why I said that it's a little thing here. But sometimes, if we ignore this kind of things, we may end up applying a result somewhere where it's not applicable, and then everything starts to go wrong. Okay, so don't do that. Here there is no problem. So we can apply our usual tan formula. One minus tan x times tan minus y. Now if you go back, we haven't mentioned this one today. If you go back to your previous sections, there you will see that just like sine, the tan function is also such that the minus comes outside. It is an odd function. So that's how you have tan x minus tan y divided by 1. If 1 minus comes out, that becomes plus with this minus. Okay, so that's how we have this formula also. So let's just stop everything here itself. Now before I really quit let's just have a brief discussion about why we even need these functions. Of course, they are mathematically interesting, but besides being mathematically interesting, they are also applied heavily. And I say heavily because there are so many phenomena in nature which are periodic, right? Periodic in the sense that they are something where something happens again and again. For example, the planets moving around the sun, or electron moving around nucleus, or in fact a nucleus vibrating about its mean position, the seasons, most of the things that you will see, in fact waves themselves, electromagnetic waves, things just are such that the same thing happens again and again after some intervals of time. So these are periodic phenomena, and the thing is such that these are the functions that capture that phenomena because they also oscillate between their values. And that is why whenever you see a mathematical model of some kind of periodic phenomenon, either you will encounter sine or cos or a combination of these things. So that is why, apart from being interesting mathematically, theoretically, practically also they are extremely valuable. That is why we need these things. So with that, let's just end this video. And the next upload is of course next Friday. It's not exactly an upload because we are doing calculus and there we are still solving problems. So we will do that on Friday. So until then, this is me, Lucifer from A Mathematical Room. Have a nice night.